Swayam Prabha. Digital India. Educated India.
Now, we have the data set ready. For the data set, right, you derived some features. Output we know, right. For example, if you know if you make a data set, right, if you take a stability, this will tell you, okay, this is stabilizing and destabilizing, right. In this case, you can use various methods. You can use statistical methods or the machine learning techniques. For example, take machine learning techniques, right. What is a machine learning technique? Right, this will fit the data. For example, machine learning techniques fit the experimental data for the stabilizing or destabilizing. So, this is the stabilizing and destabilizing. Here you have the features, right. For example, alanine is mutated to valine. They take this mutant residue, mutated residue, the position and some other information. For example, where it is located based on secondary structure or based on the accessible surface area. They take all this information, and here you can see the machine learning technique, right, and fit some of the parameters which you give in the input and the map with this output. So, they will give the mapping between the input and the output. So, they are very popular in several biological applications, because machine learning techniques work far better than the statistical methods, right. So, the performance is also very high. So, how it does? So, for example, this is the x, this input, and here is the output. So, if you this is the learning algorithm, this is your machine learning techniques. For example, neural networks or support vector machines, right, or the classification and regression tools and so on. So, this will with this y it will learn and change all the weights, right, and then again put into this machine learning again. So, then with the new weights they train this data and finally give the output. So, they repeat again and again, finally they give unless you get the best performance. This is how the machine learning techniques work. So, one is the neural network, right. I just tell you the basics, right. So, here they have three different layers. One is input layer, right, and this output layer. This is the what we want, this is the what we give. So, there is an input hidden layer. In this the hidden layer is connected with this input layer as well as the output layer, right. You can see the completely connected networks, right. So, they assign some weights, right, and based on these weights finally the output layer they will tell whether this belongs to any particular class. For example, here we give alpha or beta or loop. So, depending upon the numbers you get, they will assign, okay, if you this finally this can assign as helix or this is strand or it is a loop and so on, right. So, this is how it works. So, you can see the each node is connected to all nodes in the preceding layer. This is the connected network, right, it is fully connected, and you assign the different weights, and finally based on these functions you can see this is on which class. This is another one that is called support vector machines. So, I will give you the details with the equations in the next class, right. So, it is also a very popular algorithm, so widely used algorithm. So, it is a kind of learning algorithm, right, which right has two set of values, for example, positive negative labeled vectors. They can classify, right, these positive negatives, and using this information they can classify the unlabeled test samples, right. The SVM, right, this learns a classifier, right, by mapping the input training sample in the possibly high dimension feature space and seek a hyperplane which will separate two examples, whether it is a positive or negative. For example, if you see here, this is the dots, this is for example is a positive and this is a negative. So, there are various ways to set the hyperplane. For example, put the hyperplane here, can it separate correctly? No, right, because it is the only shown all as other side. For example, if you put this line hyperplane 1, this you can separate, yes. So, if you have another line here, which one is better? These 2 and 1 and 2 both can separate, which one is better? This one, right. Why this is better?
Because the distance.
Yeah, distance, right. If you see the distance from this one and this one and this one, this is this guy. So, in this case if the margin is wide, then even if something happens here or here, right, in these black ones, then you can discriminate correctly, right. So, they have these vectors. So, make the margin as wide as possible, right, and make other things as one group as possible, right. So, this is how the support vector machines work, right. You can use straight lines or you can use any type of nonlinear fits you can do, right, to classify the two different classes. Okay. So, now we have the data. So, we have the data set. From the data set we derive features, and the features we give in the machine learning techniques. Finally, we can get the output. Now, the question is whether the output we get that is reliable or not, how far the output matches with the input with your experimentally known data, right. For example, 100 data, right, we can know this stabilizing and destabilizing, and the output we get 100 results, then how far they correlate, how far they coincide with each other, right. It is a kind of two-state problem. So, you can have two groups, right, one is you can see one is the positive group, one is negative group, right. If this is experimental is positive, right, and the predicted is also positive, then we take this as true positive, right. For example, a mutation stabilize the protein, right, and you predict it stabilize the protein. So, both are same. So, in this case it is positive, right, because it is taken the stabilizing is considered positive, that is true, right. So, this is true positive. For example, if the experimental it is negative, but you predicted as positive, right, this false positive because you predicted as positive, but that is not correct, that is wrong. So, this way is called false positive. With experimental is plus and the predicted is minus, right. So, this is not correct, is false, and predicted is negative. So, this is false negative. Then if it is negative experimental and predicted minus, then this is true because both are correct, both are in this case it is negative. So, in this case it is true negative. So, we can assess the values, right, the experimental and the predicted into 4 groups: true positive, true negative, false positives and false negatives. Among the 4, which 2 are the correct one, which 2 are the wrong ones? These 2 are correct and these 2 are false predictions, right. So, in this case based on these measures we can define different terms called sensitivity, specificity and accuracy. Sensitivity is the one which can deal with the positive data set, specificity is with the negative data set. So, sensitivity you can see this true positive divided by true positives plus false negative, that is for all the positives. Then specificity you can say true negative divided by true negatives plus false positives, right. So, you can calculate sensitivity and specificity. Accuracy you can calculate, right, this is a total number of instances and total number of positives, okay, this is the correct one, to any t is also the correct one, right. This is a total number of samples, right. For example, if you have 100 samples and 70 is correctly predicted, accuracy will be 70%, right. So, I give one example here. So, here we have the 2 different sequences, one is experimental and the one is predicted. So, you can see B is you can say binding and this case is positive, B is positive and N is negative. How many true positives? True positives means what do you mean true positives? Is positives predicted as positive. How many true positives?
5.
4, 5. How many false positive? Predicted as plus 2.
3.
Oh, this also right. 3, 6. True negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17 and the false negative 1, 2, 3, 4, 5, 6, 7, right. If you do this, what is sensitivity? True positive is 5 divided by true positive plus false negative, false true that is 12, right. 12, 5 by 12 equal to 0.4 approximately, you can do approximately 0.4. Then specificity, true negative is 17 plus false positive, that is 23, 0.7, 0.8, 0.7, okay. Right. So, that is accuracy, true positive plus true negative, 22 divided by 35, right. This is approximately 0.5, 0.6, 0.6, okay. So, now we can see that, so it is biased with the good to predict the true positives or exclude the true negatives, right. If you see this 0.4, sensitivity is 0.4, specificity is 0.7, which one is higher? Specificity. So, in this case you can better to get the false true negatives, right, than the true positives, right. Then here it is only 0.4, right. So, this will tell you if you get the accuracy you can see 0.6, but sometimes the accuracy is biased, right, depending upon the data sets, for example unbalanced data sets. So, I show another example I will show you. If there are 100 residues, 90 are binding, right, and 10 are non binding, right, there is 100 residues, n equal to 100, binding equal to 90 and non binding equal to 10, and the program identifies all the 100 as binding, right. What is the accuracy? 90%, because 90 are correct, right, out of 100 90 is correct. So, in this case the accuracy is 90%. This method is good? Is not good, right, because if you see the accuracy this is good, because 90% is very good, right, you can use it. But if you on the other hand if you calculate the sensitivity and specificity, right, this accuracy, what is sensitivity? 90 are binding, so all the 90 are predicted correctly, so that will be 100%, right. So, what is specificity? 0%, because nothing is predicted, right. So, if you see these two numbers, then you can see that this is not a really good method, because it is completely useless method, because specificity is 0. So, in this case if you develop a method you have to make sure that your accuracy lies between sensitivity and specificity, and there is a balance between sensitivity and specificity. And another way is you can get the average, take sensitivity plus specificity by 2, in this case what is the number? 50. So, in this case it is just random, right, because two state classification, right, randomly if you get the values you will get 50%, right, this is completely random. So, another method you can use the ROC, right, receiver operator characteristics, right. In this case you can calculate from this area under the curve, just I will explain now, right. So, likewise you can have the different methods, right, to see whether your method is good or not. So, not just with the based on accuracy, you will look for sensitivity or specificity or accuracy, or you can get the balance between the sensitivity and the specificity, right, to get the performance. So, here I do one of the results I show here. So, we take statistical, here we use statistical methods and machine learning techniques, right. Statistical methods I discussed earlier in the classes, right. We use the composition and get the new protein, just compare with the group A and group B, and based on that we decide. So, if we see this one, here the data set is 2008 positives, and this is the negative data set, this is a plus and this is a negative data set, and the most of the statistical methods, right, they try to identify correctly these positives, right, with high sensitivity, right, correctly identify the positives. So, on the other hand if you use a machine learning techniques, the same data set, right, if you use here it is biased with these negatives, right. So, here 18 means the 8 amino acids excluding these 2, 10 pairs which are given in these pairs. So, if you do this, here this is statistical methods is less, here you can see the specificity is high, right, you can see excluding right, non-TBS. So, from this one you can see that whether you use machine learning or the statistical methods, right, here the statistical methods predicts the positives correctly, and the machine learning they excludes the negatives correctly. So, why the machine learning excludes the negatives correctly? Yeah, because mainly because the data sets, because here you can see bias, this is 200 and this is 900. So, right. So, this is more than 4 times higher. So, to improve the performance they are biased with this non negative set. So, this way they improve the performance. So, you have to be sure that there is a balance between these two, otherwise if one is high with this negative sets or the positive set, then the reliability is very less. So, that we need to check with the accuracy along with sensitivity and specificity. So, these are other performance, for example, the false positive rate or the precision F score, Matthews correlation coefficient. Okay, this also you can use to measure the performance of your particular your method. So, this is another one. This currently is widely used, because if you go for any classification problems, now reviewer immediately will ask, okay, what is ROC, what is the AUC. So, here this is the receiver operator characteristics, right. This is a curve, right, by plotting the sensitivity of the true positive rate against the false positive rate, right. You can write the false positive rate at the x axis, or you can versus the true positive rate in the y axis, right. You can draw and then see how far your curve goes. I will show the curve just right now, and what is the area under the curve. So, for this case you need two data, not just two data, two sets of data, right. You need the true positive rate and the false positive rate at different thresholds, not just one threshold we get one number. So, we need to change the threshold, right, and get this set of data. Using this set of data you can make a curve. So, then if you make a curve, then you can see the area under the curve, that is called AUC. This will estimate the performance of your particular method. I will just explain. So, for example, you can see this x is your input, and you do any classification model, and finally you get the output, right. Now, you take any decision function, then if this is greater than or equal to your threshold, for example 0 or 1, then you can take this yes as positive, and if it is no, then this is negative cases, right. You can see the output class based on your decision function, and you can take any cutoff to decide whether this is the type x or type y, right, A 1 or 0. So, now we can take the binary classification. For example, we have the A as positive and B as negative. If the threshold is 0, threshold is 1, for example, threshold is 1, then what is this class? For example, it is more than 1, this is A. If it is less than 1, it is B. So, in this case what is the class? Right, this is B, right. So, everything is B, this B, 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 B. Why everything is B? Because everything is less than 1. If the threshold is less than 1, the threshold you put 1, so everything less than 1, right, then this case everything is B. Now, you can calculate the sensitivity. What is sensitivity to positive by positives, but no A's are correctly predicted. So, it is 0. So, this is 0. Specificity, how many B's in the data set? 4 B's. How many B's are correctly predicted? All the 4 are correctly predicted. So, 4 by 4 this is equal to 1. So, we take the threshold 1, right, sensitivity is 0, specificity is 1. So, take the false positive rate, this is equal to 1 minus specificity. So, specificity is 1, so this is equal to 0. For example, the threshold is 0.8. What is sensitivity? How many true positives if it is 0.8? If it is 0.8, this is correct and this is also correct, right. So, 2 by 4, this is 0.5. In this case, this is wrong. So, 3 by 4, this is equal to 0.75, right. This is the 2 by 4, this is 3 by 4. Likewise, if we take a threshold 0.4, sensitivity is 0.75 and specificity is 0.5. Specificity is 0, just other way around of the threshold 1. So, this is equal to 1 and this is equal to 0. So, you can get the different threshold, you can get the sensitivity and specificity, right. So, now you can vary in threshold value, we can see a balance. If you see the threshold 1 is completely biased in one side, or the threshold 0 other side, but if you make the intermediate thresholds, right, sometimes it is better in the specificity or sometimes it is better in the sensitivity. On the other hand, other specificity is also better, right, a sensitivity 0.75, but specificity is also good. If you see these two, right, if you take the average, here we get 0.5, here you will get 615. So, this is better, right. So, you can change the threshold and then see how the performance varies. So, you can see the ROC is a sensitivity as a function of false positive rate, just you mentioned. What is false positive rate?
1
minus specificity, so that is also right. So, now you can see this is the data I showed earlier, right, with the different threshold you can get the sensitivity, specificity and false positive rate. So, where is false positive rate and the sensitivity? So, what is the value for first plot here, first one, where this place, right. So, you can see here because 0 0 this place, and the second one 0.5, right, is 0.25, right, and third one is 0.75 and this is 0.5, and the last one this is 1 and 1, right. You can get this curve, right, if you get this curve, right. So, here now this is the complete graph. So, here this is a place where we can see the curve, right. You can see how much is this is good, right. This is another example how what is the minimum value the AUC will have, what is the maximum value the AUC can have, right. If you make different curves, right, like this different curves, what is the maximum value it can take if you curve goes like this, 1, or the curve goes like this, right. So, I will show the examples. So, for example, you have 3 different functions. So, 3 different colors here, right. So, you can see how it goes, right. So, for example, with the red one, right, you can see it is completely straight. So, it occupies the full space. So, for the red one, what is AUC?
1
is 1, because this is the curve, right, the complete space, that is 1. If we take the blue one, it is completely random because both the values are the same, right. In this case, it is 50% of this full square, with 50% means this is equal to 0.5, right, like a square, this is just 50%, right. So, this will be 0.5, and if we take the magenta one function b, so what will be the value? That is anywhere between 0.5 and 1. So, if you look at this, it is very close to here, this for example you can see this is 0.7 or something, right, you can say this value is 0.7. So, from these numbers we can tell this is the balance between sensitivity and specificity, and from these numbers you can say whether your method performs good or not, right, for any classification problems. So, these are the classification problems. Now, the next one is real values. For example, if you have the binding affinity of 0.2 kilocalorie per mole or the stability of 1.2 kilocalorie per mole, right, how can we do that? So, in this case we can do the regression equations, right. So, the y axis you can see this is your experimental data, and x axis you can see the various important features. For example, if you want to have the physiological conditions and the growth of a plant, right, this in agriculture field it is very important, right. If you make a plant, so everyone likes to grow, right. So, we cannot grow apple here, right. So, likewise we need to know which conditions this plant can grow and which conditions the plant can give the fruit. So, there are some of the various aspects, I listed some of them. Okay, for example, what is the maximum temperature at that place, right, what is the minimum temperature. For example, some plants require high temperature, some plants require very low temperature. So, in this case if you plant which requires high temperature, so if you do it in the cold countries you can get, it will not grow, right. So, that is the maximum relative humidity and the minimum relative humidity, or you can see the rainfalls, what is the approximate rainfall, and you can see rainy days per week, right. If you go to the agriculture department you can get this information, so any local place you can get the information. With this information you will also tell that okay, if you do it in June to September, this is the case and the yield is 70% or yield is 100%, right. Then we know the conditions and we know the yield, accordingly you try to plant, right, in that conditions, right. Either you have to artificially you have to maintain the temperature, or you have to think okay, this is the season where we have the temperature in this range and we can do. This is the reason sometimes it fails. We expect, right, mainly June and July will get rain. So, this way we plant, but if we do not get rain, then we do not get the fruits, right, we do not get the yield. Likewise, we can use this technique, right, this is your experimental growth of a plant or yield, and here these are your variables. How this growth depends upon the different other factors like the temperature or humidity or rainfall and so on. So, we can use the principal least squares already discussed earlier in the previous classes. So, I do not want to explain more, right. So, use this one and then finally get the coefficients. If you set the coefficients, then you can see probably if this is the temperature and the humidity, then what will be the yield. At least if you do not 100%, right, if you get 80%, then we can try, right, because the worst case how much it can go, right, because for we expect rain, if it rainfall is less than what we expected, up to which conditions we will get the profit, right. If you very worst case, then we do not do that, right. This is how we can do this. So, now how to estimate the reliability, right. So, you can get the correlation between the two variables. For example, here we have these experimental values, the growth of the plant, right, or here these are predicted ones. Then how far we can with this features, right, what is the correlation, which is highly correlated or less correlated. Highly correlated means you can use this equation, right, for giving this new the growth of new plant with this particular conditions. This we have mean absolute error, this also we discussed in the last class, right. So, this we can get 1 by n is sigma positive predicted minus experimental, take the absolute values, right, and take the average, then we will get the mean absolute error. So, mean absolute error should be high or less? Less. Correlation coefficient should be high, right. So, if you get the high good correlation and should go the less error, then you can see your method works fine. So, now the next question is, okay, we need when you make the machine learning techniques, we have to check the number of data as well as number of features, right, because last time in the QSR also we discussed, right. So, what is the rules for the QSR with respect to data and the variables?
Data should be 5 times more.
At least more than 5 times, and essentially if you take the ideally if you see 3 to 5 features, not more than that. So, if we see the number of data, for example, we have the 20 data or 30 data, and if fit with 15 features, for example, we have 30 data and fit with 15 features, we will get good results. You will see the accuracy, sensitivity, specificity, ROC, and you can get very high values, but this will work for the new data, right, because it will not work, because here you have see that you can 30 data are fitted with 15 features. So, you can cause overfitting, right, because even if one parameter can take care of 2 data, all the 15 parameters can take care of all the 30 data, accuracy will be 100. But new one comes, if you won't fit within any of these 2 values, then completely that is totally wrong, right. This is the reason why we need the less number of features and more number of data. In this case, the small number of features could account the more number of data, even if the new one comes, because the probability is very high. So, in this case it has high probability to capture the information from the new data and you can get better results. So, there is a reason why we need to have the less number of features as well as more number of data for doing any of these techniques to avoid overfitting. Now, we have to do the validation. What different validation procedures we need to do, right, because systematic validation is important, right. Usually if you do train with the same data set, we get good results, then people will be happy, okay, my accuracy 97% or 98%, so my method is fine, right. This is what we do, the self assessment, right. For example, 100 data. So, in the training you take 100 to derive the parameters, and the tests you take the same 100. So, you expect high performance or low performance? High performance. Why high performance? Because these 100 data will capture the important information and then you predict with the same set. So, whatever you capture there, then you can apply to their same, right, that you can do the test, right, will give the good results. And second, you can take the training and test set. For example, take some part, for example, 70%, 70 training and 30 test. So, then you capture the features only from 70 data. Already we discussed about data set, it is completely non redundant. In this case, with this 30 are the also non redundant, not related with the 70, and in this case even if the features captured from this 70 are able to predict the 30, then we can trust if a new one comes is possible to capture. Then you change this training and test 80-20 or 60-40 and see even if the less number of training, if you can predict well in the more number of tests, that means whatever the feature you get from this training, that is reliable and that is important for predicting this test set of data, that is very important. So, we need to have different sets 70-30 or 80-20 or 60-40, right, we can do different sets of training and test. And the third one, you can do this n-fold cross validation. That means if you have 100 data, you made into, for example, take 5-fold cross validation. right. So, we divide into 5 groups, right, you can see into 5 groups 1, 2, 3, 4, 5 and train 4 and test, right. So, 80 you train and 20 you test, but you do it for 5 times, right, 5 times. So, that each one will be at least one time in the test, right. In this case that is not the case, something is training then is the test, but it is not the other way around, right. In this case here if you do the cross validation at least one time all the sample will be at least once in the test. The more rigorous one, this is a jackknife test. In this case with 100 training data, take 99 to train and 1 to test and repeat 100 times, right. So, then you do it for 100 times, then see whether the performance, after that you get all the output. So, you get the performance comparing with the experiments, however you can do it in the jackknife test. Then split sampling, this is random, randomly choose some set of data for training and get the features, and using that you develop a model and use the model for predict the remaining ones. You can take any randomly take the split and you can do that. For example, if you take this 65, 35 and so on, any numbers you can take. So, now if you do this, right, for example, if you have good results, then the question is whether your method is better than other methods or not. If you develop any method, you have to show, right, your method is better, right, otherwise immediately they will ask, so what, right. So, you got something, so what is the importance, why do you need to use your method. So, you have to show in different ways that okay, data is the method is better. Then you need to check the literature and see what are the other reports available in literature. If yours is the first one, then it is little easy, because you can say this is novel, this is the first report. So, we could get the accuracy of up to that much percentage. If already reports are available in the literature, then you have to compare on different aspects, or you can use different data sets, you can measure with different measures, different validation procedures and different new data. If you have a new data set and your method can correctly predict and other methods are not able to predict, then you can say that if we get any new data, our method will perform better than other methods in the literature. So, you have to compare with other methods, different ways to comparison, either you compare with the same data set what they use mainly for the test, or you can select the data which are currently available, newest data that you never used, they also never used, and you compare common data set, right. Otherwise, sometimes we do not know which data set they use for training, but in this case your training and their training will be different. So, you have to make sure that you have some common data set to compare with the different methods. Then once it is done, your method is performing the best, then we can try for some applications. And how do the others know that you have a method? In this case, you can develop a server, right. So, you have the applications that should be user friendly. So, when you are satisfied with your method and compare other methods in literature, so for the applications you have to construct a server, so that others can also use your method and see whether your method is reliable and how to compare their data also with your method, right. So, with the beneficial to the other researchers, right, you have develop a server that should be user friendly, because if anybody access your server, right, already we discussed about database, that what are the features considered to develop a database. Likewise, if the other researchers like to use your server, that should be user friendly, so that they can get the results quickly and what they want, then we need to provide the data. Or you can do the effect algorithms, right, put in the server, and in this case you can give the reliable results, so that others can use your data set, and that will be beneficial to other researchers in this field. So, we discussed various aspects, right, two different types of problems. What two different types of problems? Classification problems and the real predictions. Then what are the various aspects you need to consider? The first one is data set. You have to be very careful about developing data set, because that is very important and very sensitive. Once data set is done, and then go with the features depending upon the problem you are working on. So, you have to derive the features. Once you have the features in data set, and then develop a method, right, you can put in the machine learning or statistical methods, so that you can predict the output. Then you need to assess. So, various measures to assess the performance. What are the various measures? Sensitivity, specificity, accuracy, ROC curve, right, area under the curve. So, from that you can assess the performance of your method. right. Then you have to validate. So, you have the n-fold cross validation or the jackknife test, right, or the split sampling, could be any cross validation methods, right, and see whether it performs better or not. Once everything is fine, then go with the comparison with other methods in literature. So, see how far your method could perform better than other methods in literature, and then you make a server, right. In this case, everybody can use, several users, right, they can use your data set to your server, so that they can predict for their values and compare how far our method is better than other methods in the literature, right. Then they can use it, because all the bioinformatics problems, why we do it, because have some potential applications, right. For example, for the drug design or different, like I mentioned earlier, like the cancer mutations and different aspects. So, your methods works fine, and if you have a server, then they can use this as their input, and this can be used, right, for doing any experiments. So, we will give the first hand information for designing various experiments, right, that will be useful for the experimentalist also, right, to design their own experiments based on the data obtained from any new methods, right. Thanks for your kind attention.